Have you ever wondered how a computer, which really just understands on and off, can process something as complex as language? Well, it all starts with rules. Really, really simple, but incredibly powerful rules. Today, we're going to build our very first thinking machine, right from scratch. A machine that can spot patterns, which is, the absolute foundation of all computing.
All right, so here's the game plan. We're going to start with the big picture, the different levels of computational power. Then, we'll get down to the nitty-gritty, the actual building blocks. After that, we'll build two kinds of machines, see how they stack up against each other, and finally, we'll check out what else they can do besides just giving a thumbs up or thumbs down.
So, before we can get our hands dirty and build this machine, we kind of need a map. We need to know where it lives in the whole universe of computation. Because, let's be real, not all problems are the same, and neither are the machines we build to solve them.
And this is that map. It's called the Chomsky hierarchy, and it's basically a power ranking for languages, based on how complex they are. The further you move out from the center, the more powerful the language and the machine you need to understand it gets. We're going to start our journey today right in the middle, at the foundation. Type 3, the regular languages. These are the ones understood by the simplest machine of all, the finite automaton.
Okay, let's dial it all the way back to the absolute basics. We're going to see how you actually build a language from the smallest pieces imaginable. It's like learning the ABCs before you try to read a novel.
Everything, and I really mean everything in this world, starts with a symbol. Think of it like a Lego brick or an atom. It's the smallest possible piece. You just can't break it down anymore. A 0, a 1, the letter A, those are all perfect examples.
So you take a handful of those symbols and you put them in a set. That's it. That's your alphabet. The most famous one, of course, is the binary alphabet, just 0, 1. It's the language every single computer speaks.
Now, once you have your alphabet, you can start putting those symbols together in a row, and what you get is a string. It's just like using letters to make a word. 01101 is a string made from our binary alphabet. It's really that simple.
And that brings us to language. Now, in computer science, a language isn't like English or Spanish. It's just a set of rules that decides which strings get to be in the club and which ones are left out. For instance, you could have a language of all binary strings that have to start with a 1. If a string follows the rule, it's in. If not, it's out.
So, we have the rules for our club. Now, we need a bouncer at the door to enforce them. Let's build one. Meet the deterministic finite automaton, or DFA for short. It's strict, it's predictable, and it is incredibly reliable.
Think of a DFA like a very simple flowchart, or maybe one of those old choose-your-own-adventure books where every choice leads to exactly one page. It reads a string one symbol at a time, and for every symbol it sees, it knows exactly what to do next. There's no choice, no ambiguity, no guesswork. It just follows one single, predetermined path, and when it's done reading, it's either in an accept state or a reject state. That's it. Yes or no.
Okay, that DFA was pretty rigid, right? But what if we loosen the rules a bit? What if our machine could explore possibilities? Let's meet the DFA's more flexible cousin, the non-deterministic finite automaton, or NFA.
Okay, the whole magic trick is right here, in this one little difference. With a DFA, when you're in a certain state and you read a symbol, you go to one specific next state. But an NFA, it can go to a whole set of next states. It can basically split itself into multiple copies and explore all possible paths at the exact same time. It's like a parallel universe explorer for strings.
Now, that ability to explore multiple paths at once, it sounds like it should make the NFA way more powerful, right? And you'd be correct, just not in the way you might think. See, it turns out that anything an NFA can recognize, a DFA can recognize too. The real jaw-dropping difference between them isn't what they can do, but how efficiently they can do it.
So let's throw a real curveball at them and see what happens. We want a machine that says yes to any string where, let's say, the third to last character is an A. Now this is tricky because the machine is reading from the beginning. It has no idea when the string is going to end until it's already over.
Okay, now check out this table. For most of these common jobs, the DFA and NFA are pretty neck and neck in terms of how many states they need. But then, look at that last row. For our specific problem, finding the nth symbol from the end, the difference is just astronomical. An NFA needs just n plus 1 states. The DFA, it needs 2 to the power of n states.
And we're not talking about a small difference here. This is an exponential explosion.
For an NFA to check the 20th to last character, it needs 21 states. A DFA would need over 1 million. This is the incredible power of non-determinism. It's not about being able to solve more problems, it's about being able to solve certain problems exponentially more efficiently. That ability to guess and follow all paths at once is a real superpower. All right, so we've got machines that can say yes or no to a string. They're great bouncers for our language club. But what if we wanted them to do more? What if we wanted them to actually produce some kind of output? Well, it turns out we can do that, and we can even optimize them to be the best possible versions of themselves. So, let's meet a couple of new players. First, the more machine. Its output is tied only to the state it's currently in. Think of a vending machine. The sold-out light turns on simply because it's in the empty state. Then you have the Mealy machine, which is a bit more reactive. Its output depends on both its current state and the input it just received. That's more like a traffic light turning yellow. It's not just yellow because it was green. It's yellow because it just got the change now signal.
And here's something really profound. It turns out that for any regular language, there is one single unique DFA that has the absolute minimum number of states possible. It's the perfect, most streamlined version. The Myhill-Nerode theorem gives us the theory behind it. Essentially, we can find any states that do the exact same job, that are basically twins, and merge them into one, boiling the whole machine down to its most efficient form.
So here's the big takeaway. Finite automata are fantastic for recognizing simple patterns, but their greatest strength, their simplicity, is also their greatest weakness. They have a finite number of states, which means they have no memory. They can't keep a running count of anything. That makes it totally impossible for them to recognize a language of, say, an equal number of A's followed by an equal number of B's, or to check if all the parentheses in a piece of code are balanced. And that leaves us with one final big question. To solve these more complex problems, what kind of machine would we need next?